Today, we are going to discuss on the second application of Gauss's theorem. Second application of Gauss's theorem we are discussing today is electric intensity due to an infinite plane sheet of charge. Here, charge is distributed in the form of a plane sheet. Let us consider an infinite thin sheet of charge with a uniform charge density sigma coulomb per meter square. That is, charge per unit area is sigma. This is an infinite charge sheet. The plane charge sheet in which the electric field lines emerges normal from the surface to both sides equally, as shown in the figure. Let us consider a point P at a distance r away from the charge sheet, where the electric field intensity is to be determined. Let E be the electric field intensity at P. To find electric field intensity at P, let us consider a Gaussian surface. Here we are considering a cylindrical Gaussian surface which is passing through this charge sheet. It has two base surfaces. The base surface is having an area ds and its wall passes through the charge sheet. The base area, one of the base area include that point P, where the electric field intensity is to be determined. This elliptical surface extending both sides equally. So, here the electric field intensity at the base surface A and B are same, since it is equal distance away from the plane sheet of charge. The electric fields crossing the surfaces A and B, but the electric field is parallel to the curved surface. So, the flux through the curved surface is 0. Here we have to consider only the flux through the base surfaces. The electric flux through the end surfaces A and B is equal to E dot ds plus E dot ds. So the total flux through the Gaussian surface phi is equal to E dot ds plus E dot ds. And you know, this flux is or electric field intensity to the surface B and A are normal to the surface. So we can write E dot ds as E ds. Therefore, total flux is equal to 2 E ds. Find how much area is inside this cylindrical Gaussian surface. That is, ds area of this charge sheet is inside this Gaussian surface. Therefore, the total charge enclosed by the Gaussian surface is sigma ds. You know, sigma is the charge density. Let us apply the Gauss's theorem. Total flux is equal to 1 by epsilon 0 into total charge enclosed by the Gaussian surface. Gauss's theorem, phi is equal to 1 by epsilon 0 sigma ds. You already derived an equation of pi. Pi is equal to 2e ds. These two equations are same. 2e ds is equal to 1 by epsilon 0 sigma ds. Rearrange the equation. E is equal to 1 by 2 epsilon 0 sigma. Equation E is equal to 1 by 2 epsilon 0 sigma. In this equation, the magnitude of E is independent of distance. There is no term for distance. It depends only on permittivity and charge density. Consider a plane conductor, then the total charge enclosed by the surface will be 2 sigma ds. Because charge is present on other side of the conductor. If it is a conductor, charge is distributed on both sides of the conductor. So the equation becomes E is equal to 1 by 2 epsilon 0 2 sigma. That is equal to 1 by epsilon 0 sigma. This is the case of a plane conductor in which both sides the charge is distributed. Electric intensity due to two plane sheets of charge. Consider two infinite plane parallel sheets of charge A and B with the uniform charge densities sigma 1 and sigma 2. We have to consider three regions separately. To find the electric field intensity at these three different regions by using the superposition principle. Electric field intensity due to charge sheet at A having charge density sigma 1 is given by the equation EA is equal to sigma 1 by 2 epsilon 0. Similarly, electric field due to charge sheet at B having charge density sigma 2 is given by the equation EB is equal to sigma 2 by 2 epsilon 0. Here we have to find electric field intensity at the three regions separately. Let us find electric intensity E at the region 1. Here, the electric field is in the same direction. If you are taking this direction as positive, then this can be taken as negative because electric field is a vector. So we can write minus EA plus minus AB is equal to minus sigma 1 by 2 epsilon 0 plus minus sigma 2 by 2 epsilon 0. So we can write it as minus sigma 1 plus minus sigma 2 divided by 2 epsilon 0. This is the electric field intensity at this region. It is in the negative direction. The electric intensity E at the region 2. Here, the electric fields are in the opposite directions. EA is in the positive direction and EB is in the negative direction. So we have to find the electric field intensity at that region. Is EA minus EB is equal to sigma 1 by 2 epsilon 0 minus sigma 2 divided by 2 epsilon 0. That is equal to sigma 1 minus sigma 2 by 2 epsilon 0. Now we have to find the electric field intensity at the region 3. Here the electric fields EA and EB are in the positive directions and also in the same direction. So we can write the total electric field intensity at this region is EA plus EB is equal to sigma 1 by 2 epsilon 0 plus sigma 2 by 2 epsilon 0 is equal to sigma 1 plus sigma 2 divided by 2 epsilon 0. The electric intensity E at the three regions are shown here. At the region 1, it is EA and EB are in the same direction, but it is in the negative direction. So we can write it as minus sigma 1 plus minus sigma 2 divided by 2 epsilon 0. At the region 2, EA is the positive direction and EB is in the negative direction. So we can write it as sigma 1 minus sigma 2 is divided by 2 epsilon 0. The region 3, EA and EB are in the positive direction. So at this region, the total electric intensity is sigma 1 plus sigma 2 divided by 2 epsilon 0. Two charge sheets are charged uniformly with equal and opposite charges. That is sigma 1 is equal to sigma and sigma 2 is equal to minus sigma. That is the charge sheet A is having a charge density sigma, positive charge, and the charge sheet B is having charge density minus sigma, that is negative charge density. So what happens to the electric field at these regions? Let us see the equation. Sigma plus minus sigma divided by 2 epsilon 0. Sigma minus minus sigma by 2 epsilon 0. At the region 3, sigma plus minus sigma by 2 epsilon 0. Now we can see the electric field is only remaining in between the charge sheets. No electric field is outside the charge sheets. The electric field is only existing between the charge sheets of two charge sheets of equal and opposite charges is equal to sigma by epsilon 0.